my name is Joachim Meyer. I am image processing and GPGPU engineer at STEM Imaging. Over the last year, I did a project on evaluating 4 different GPGPU APIs in the context of image processing. So why do we actually need to evaluate GPGPU programming models? Well, there's just too many. We have 5 Khronos standards that support GPU computing. We have NVIDIA's CUDA, we have AMD's ROCm, we have OpenMP with GPU's capabilities, as well as Microsoft's DirectX 12. But which one is the right one for the super cool new project that you're planning? Well, there's not one answer, but I will try to present you some metrics that you might find interesting and helpful in deciding which one to choose. So I'll first give you the selection of the 4 APIs I will compare, then I'll present you the background of the test project I set up, and afterwards I will compare those 4 APIs on the 3 metrics: performance, usability, and platform independence, and that I will conclude afterwards. So let's start with the selection of APIs. I chose the 3 Khronos standards: Vulkan, OpenCL, and SYCL, and as a reference, as it's used widely, especially in scientific applications, I also chose CUDA. The test project created for this evaluation targets all 4 APIs plus an extra CPU reference implementation. The targeted device types are CPUs and GPUs, when possible through the same APIs. So OpenCL and SYCL, for example, allowed us to target both using the exact same code. The operating systems we needed support for are at least Windows and Linux, and they were both tested. The implementations I used are the most recent CUDA and Vulkan versions. For OpenCL, to have NVIDIA support, I had to use version 1.2. For SYCL, I used ComputitionCPP from CodePlay, mostly on Windows, and on Linux, especially on the NVIDIA Jetson, I used HipSYCL. And the algorithms that I actually implemented in this test project constitute a pipeline of processing images from polarization cameras. Polarization cameras produce images that have a Bayer-like pattern, but instead of filtering colors, those 4 pixels are filtering 4 different polarization directions. So you can get some information about how the light is polarized at which point of the image, which you can further process. Let's now start with the actual comparison of the 4 APIs. The first point is performance. And this is the only slide I have about performance, because I consider it not being the most important decision factor. The performance is mostly limited by the hardware, and the small differences that you find in those graphs usually is implementation defined. So depending on your implementation that you made, depending on the vendor drive implementation, this varies quite much, and depending on the devices you use, you can't really say which one will be faster everywhere. So you probably need to do your own testing, or you might even just ignore this as a metric, because the other metrics will influence your development time, development cost much more. So let's go on with usability. I think that's a way more important metric. And as the usability heavily impacts the implementation cost, I tried to measure this in some way. First, I tried to measure this in lines of code. This is probably not the most reliable measurement, but it's the only measurement for implementation cost that I was able to easily quantify. I have 3 different measures here. I have lines of code for a basic setup, for a realistic setup, and lines of code for a new kernel in a realistic setup. So the first one is like the really, really basic case that just is for prototypes and everything is implicit as possible and you just take what you get. The more realistic setup is actually choosing different devices or maybe checking for extensions that are available in the case of Vulkan. And the lines of code for a new kernel, that's for a realistic setup what you need to add for a new kernel with different arguments and so on. So we can see that the single source models, CUDA and SYCL, are somewhat shorter than the other two. For OpenCL, it should be noted that these few lines are only possible when using the C++ headers in the version 2 because it allows doing many things implicitly using the default arguments. The difference to Vulkan is quite high, but don't be afraid. Vulkan allows you to optimize many of those lines that you have to write here. So it's also an opportunity and not only a higher setup cost. In the realistic setup for Vulkan, I separated the really somewhat more necessary parts from the GLSL to spoof online compilation because you might also offline compile your code and then I didn't want to pollute the number with it. For us, it would be nice if we had a single programming language for the GPU and the CPU. And as we mostly use C++, it would be awesome to also be able to use C++ ideas and concepts on the GPU. So yeah, that's a measurement for us. It should be noted that CUDA and SYCL easily implemented as it's a single source programming model and everything of it is in C++. For OpenCL, it's a little bit different. You can use OpenCL as a C++ in OpenCL as a kernel language, but it's not as well supported, and you usually have to pre-compile it to an intermediate representation, which might not be as compatible with all devices as OpenCL-C is. The implicit asynchronity metric is important for me. I wanted to add here is because getting asynchronity right is somewhat difficult, and getting started easily with some asynchronity is nice, and yeah, because it speeds up your program like super fast without much effort. With CUDA and SYCL, we have a task graph implementation that provides this. With CUDA, you can also define that each host thread should define a new CUDA stream and therefore provide easy access to asynchronous operations. In OpenCL, there's also out-of-order queues, which somewhat give you implicit asynchronity. Another important factor impacting the usability of a programming model is the tooling that is available. So with CUDA, for example, NVIDIA provided many development tooling, for example, a kernel debugger, profiling, and even some integration into Visual Studio and so on. So the tooling is right at your hands and it is very powerful and major. With OpenCL, you can use some of those CUDA tools, but they are not that major. And for other vendors' hardware, you will need to use the other vendors' development tooling. So if you want to test and profile on different hardware, you will always have to use and rely on the different vendors' tooling. The LPGPU project tried to generalize this a little bit. They reused AMD's CodeXL, which is now open source, and provided a backend for mobile devices, for example. CodePlay also used CodeXL to add some SYCL-specific profiling, I think, and this is almost one of the only SYCL specific tooling I know. Otherwise, when considering SYCL tools, you can also use the tools of the backend of the SYCL implementation. For example, with CodePlay's compute-CPP, you can use the OpenCL tools that you would otherwise use for your vendor's hardware. When using HipSYCL, HIP is a portability initiative that helps you run CUDA-like code on AMD or NVIDIA graphics cards. And so, therefore you can use, as HipSYCL builds upon HIP, you can use the AMD or NVIDIA specific tooling available for HIP or for CUDA. Otherwise, SYCL also provides an interesting option to debug your kernels, because SYCL is fully compliant C++. You can just compile the SYCL code, the C++ code, and run it on your CPU. So you can also just use your usual C++ debugger to debug the SYCL code on the CPU. This will help you find many issues, but probably not all, because the environment that the code is executed on is a little bit different. When talking about Vulkan, tooling for compute-specific tasks is a little bit rare, but there's graphics tooling available. And some of this graphics tooling can be reused for compute tooling as well, for compute tasks. For example, profilers or similar. Also, there are the validation layers. These validation layers help you find issues in your host code by telling you when you didn't initialize something correctly. Also, there's an emulator, especially for compute tasks, that helps debugging your SPIRF code on the CPU. Another point to include in the discussion about development time and therefore development costs is the availability of libraries. For CUDA, NVIDIA provides many libraries that already implement some of the functionality that you might need. For example, fast Fourier transforms, linear algebra, image processing, and much, much more. Those are pretty optimized as well, so you probably find something that will help you and reduce your development cost. For OpenCL, these libraries that are available might not be as optimized for all supported devices, but there are still a quite good number of different performance primitives, as well as some more advanced algorithms. As there are not that many SYCL libraries yet that are SYCL specific, you can again use the native libraries, for example, of the backend, for example, all the OpenCL or CUDA libraries that were mentioned earlier. But CodePlay did a good job over the last few years to develop some basic libraries for SYCL as well. There are linear algebra, deep neural network, random number generators, image processing libraries that you can reuse, and also the parallel SDL was implemented in SYCL. For Vulkan, there are not yet that many compute-specific libraries, but again, there are libraries that you might want to reuse from graphics applications. For example, there's a memory allocator that can well be used in compute applications as well, because it helps you optimize your memory allocations to reduce defragmentation of your memory. Fragmentation, not defragmentation. Another metric I'd like to apply is the community support. And to measure community support, I tried to consider application adoption and Stack Overflow questions. So the application adoption tells us a little bit about how many developers are there that actually use those APIs, and therefore how many developers have proficiency and therefore might be able to answer your questions online. For CUDA, I'd say that it's pretty widely used, especially by scientists and some application developers. And it's also the de facto standard in machine learning, so you probably will find someone that could help you with your issues. For OpenCL, which is also almost as old as CUDA, the adoption rate is also very high. And I consider it being more adopted in the consumer application world by, for example, some parts of the Adobe Creative Cloud or Final Cut Pro or many other applications. Also, the Stack Overflow question count is super high for both of them, especially for CUDA, which is different for SYCL and Vulkan. So SYCL is not that old. The only implementation that actually is fully conformed is the compute-CPP by CodePlay. And yeah, therefore not that many applications use it yet. CodePlay ported, for example, TensorFlow and Eigen, where you could find some inspiration on how to develop your SYCL applications. And the Stack Overflow question count is super low at 28 questions. But it should be noted that as the vendors seem to want to push it, there are community forums by CodePlay, for example, and also other vendors are super helpful right now in providing support. Considering Vulkan, Vulkan is, as already mentioned, graphics and compute API, and therefore I have mostly seen Vulkan compute in combined applications where already Vulkan was used as a graphics rendering API and therefore could easily be extended to be used as a compute API. This can, for example, be seen in the Octane renderer. Another option where Vulkan is widely used is in mobile device applications. So, for example, Adobe ported its Premiere video editing program to Android. It's now called Adobe Premiere Rush, and this uses Vulkan as a compute backend because it's well supported on mobile devices. The Stack Overflow count here is somewhat misleading maybe, because those questions again are for graphics and for compute. Although again, some of the graphics questions also apply to compute applications. Another difference in those APIs and programming models is how the kernel code gets executable. And I want to present you that a little bit. So for example, CUDA and SYCL usually have a host and a device compiler. Those run on the same code because you need to extract the device code out of the combined single source C++ code. For CUDA, this can be Clang or NVCC. For SYCL, this depends on the implementation. This can be this is always some compiler of the implementation of HipSYCL, of DPC++, or compute-CPP, or TriSYCL, or whatever. And those usually compile to the device code to some intermediate representation. For example, PDX, SPIR, or SPIR, which is then embedded in the executable and can be delegated to the driver or runtime. For OpenCL and Vulkan, this is a little bit different. You can program OpenCL in OpenCL C or C++, depending on your version. And Vulkan can be programmed in either HLSL, GLSL, or SPIR. And depending on what you use, it of course requires different tooling. For OpenCL, you can usually, if you use the traditional OpenCL C, you can just delegate the compilation to the OpenCL driver. It will handle the whole compilation, and therefore you just load your text of the code and give it to the driver. This is very straightforward and is enables some use cases as seen in the next page. But you can also offline compile it to SPIR or SPIRF, depending on your tool chain and your targeted drivers. And you can target Vulkan as well with OpenCL if you use the cross-compiler CLSPV. This generates SPIRF, which is Vulkan compatible. When you want to program Vulkan with GLSL, which I did in my test project, you have two options to offline compile. It's Shatter-C or GLSLA. And you can also online compile your code using libshatter-c. As I already mentioned earlier, I did this, which just required some more lines. Using this knowledge about the compilation workflows, I want to present you an issue that has to be handled differently in the four APIs. It's dynamic data types, because in image processing we might have different data types coming in, because some images are in Unit 8, some in Unit 16, some in floating point. So how do we handle those? In CUDA and SYCL, we can just use the C++ features for template programming and generic programming and provide a generic implementation that works on all data types with some type deduction and so on to get the temporary data types that we need and so on. We can also specialize functions to get more performance for specific implementations and so on. For OpenCL and Vulkan, this is a little bit different, as we don't have C++ programming at hand usually. And yeah, for example, in OpenCL, we can always online compile. And what I would propose as an example is that you can use preprocessor macros to select the data type that you will need to use. For example, you can say you want Unit 8, and for your Unit 8, you might want to use Unit 32 as a temporary data type. You can just switch this depending on the data type you can give online in your online compilation as a macro. For Vulkan, you can do the same using the Shatter-C as an online compilation. But you can also offline compile. If you want to offline compile, you just do the same. You offline compile with a given macro and just give the compiled SPIRF different names and load the correct SPIRF kernels. Considering that Vulkan is very extensible and is not always compute focused, you might need to consider that Unit 8 or Unit 16 or similar non-uniform data types are not always supported. For Vulkan, this means you have to check extensions. So there's, for example, the extension that supports Unit 8 and Unit 16 storage, which enables you to only transfer those images in the smaller data types and then convert it on the GPU to full 32-bit integers and do the arithmetic on the 32-bit integers. Otherwise, even if this extension is not available, you will need to convert on the host side the complete image. So yeah, beware of that. The last point of comparison is the platform independence. For us, it's important that we don't only have one vendor that we can target with an API, but we can target many different devices. So which API or programming model can target which vendor's devices or operating systems? Well, NVIDIA develops CUDA only for NVIDIA GPUs, but it runs on Windows, Linux, and macOS, although macOS support is deprecated and not really useful as there's no new Apple devices using NVIDIA graphics cards. And also there's support for AMD devices if you use HIP instead of CUDA, but this also has many limitations, including not being able to run on Windows. When considering SYCL and OpenCL, an interesting point is that those two also support running on CPUs and FPGAs. But otherwise they are somewhat different. SYCL is mostly supported on every platform in the newest version, with some limitations on Windows, as for example, the Intel LLVM project does not yet target NVIDIA GPUs on Windows, but only on Linux. For OpenCL, the version support is a little bit not that bad, not that good. The newest version 2.2 is not conformably supported by any vendor. NVIDIA does even only conformably support 1.2. Also on macOS and mobile devices, including Android, OpenCL support might be present, but cannot be relied on anymore. Especially on macOS, OpenCL is deprecated. Vulkan, on the other hand, is well supported through all vendors, while all vendors provide drivers for the newest version, usually. The only limitation operating system-wise is that macOS and iOS do only support Vulkan via a compatibility layer, for example, MoltenVK or GFX-RS. Also, there's a portability initiative for Vulkan called SwiftShader to run Vulkan code on CPUs. Speaking of SwiftShader, I want to present you some more portability initiatives. As mentioned, SwiftShader lets you run Vulkan code on CPUs. SEAL-SPV I already mentioned earlier as well. It's used to compile OpenCL C to SPIRF that is compatible with the Vulkan runtime. This again is used by CLVK to run OpenCL on Vulkan, so it's like a Vulkan like an OpenCL driver on top of Vulkan. Then there's an initiative by Microsoft to run OpenCL 1.2 on top of DirectX 12. There is a project called CUDA that provides a layer to run CUDA code on OpenCL. There's HIP that enables you to run CUDA-like code on AMD and NVIDIA platforms. And there's HIPCL, which is a target for HIP to run the same code on OpenCL devices as well. So to conclude, I can't tell you which API you should use, but here are some of the most important metrics that I think you should consider. Also, there's a link to the full abstract on the bottom of the page where you find a decision matrix with some number quantification of those metrics. So CUDA and SYCL definitely have a point because they are single source programming models, in my opinion. It makes the development far more smoother than the separated programming models of OpenCL and Vulkan. CUDA also has very highly optimized libraries and very powerful tools. But a major drawback of CUDA is that it only supports NVIDIA devices. You might use HIP to get at least AMD support, but it stays questionable whether that's enough. And HIP has some drawbacks too. With SYCL, as I said, the single source programming model makes it very attractive. You can target multiple platforms, including specialized processors, FPGAs, and much more. And you can use existing tools and libraries from the underlying implementation or backend, however you want to call it. Yeah, one drawback I see in SYCL is that the tool chain and libraries that are specific for SYCL are not yet that mature as those for CUDA OpenCL. So that still needs some work. Considering OpenCL, you will get a cross-platform targeting programming model. You will get some major libraries. You have a rather big community, but you have to fight against not up-to-date drivers. So you can't use all cool new features on every device. So you might have to stick with older versions. For Vulkan, it's a nice option if you want to target mobile devices or also already have Vulkan in your graphics API. It also is fully OS and GPU vendor independent. So that might be pretty important for you, but it only targets GPUs as mentioned and CPUs. It has a rather high setup cost, but as I already mentioned, all those code that you have to maintain also leads to the opportunity to have many points of interest where you can start to optimize your setup. Also, the lack of compute-specific tooling and libraries is a little bit sad, but might change in the future. Speaking of the future, I want to present you some future prospects as well to conclude. For CUDA, I expect that it will stay one of the most innovative APIs because it's directly developed by NVIDIA. I think that new GPU features will directly get supported in CUDA. Also, other optimizations and feature updates will follow gradually. Regarding portability, I somewhat expect that at least the HIP runtime will be ported to Windows at some point, so that CUDA-like code at least would get more portable in total. For SYCL, I expect the implementations to mature much more, so they will get more stable and faster. I also expect to see some extended hardware and operating system support, for example, getting the Intel LLVM implementation targeting NVIDIA to target Windows as well. Due to the removal of OpenCL as a conformance-required backend, I also expect to see some more SYCL implementations that target other platforms to get some even more platform independence. Also, I expect some more SYCL-specific tooling to appear. Also, a talk here at IWOCL, I think, will talk about a SYCL debugger by Intel, for example. And I guess we will hear some more news here at IWOCL. For OpenCL, I hope that the new standard OpenCL Next will improve vendor support again, so that there are many new features that can be used on more GPUs and devices. Also, I expect OpenCL to get some support for new hardware features again and again, but this will probably be mostly due to extensions. Also, I expect some higher level kernel languages to be supported better, like C++ will get some easier path to work on more GPUs. And I also expect some more news here at IWOCL. For Vulkan, I would say that it will stay a very widely supported opportunity to use some compute capabilities of GPUs. I think that it might even be somewhat extended in its compute capabilities. So it can be used as a portability backend for some more APIs, like to remove some limitations of CLVK, for example. I also expect at some point to see some more compute-specific tooling and libraries. Yeah. Also, Vulkan will be one of the fastest APIs of those to catch up with new GPU features. Thank you very much for watching. I hope you've learned something about the 4 APIs and got some idea on which API you might choose for your next project. If you have done some similar comparison on those less performance-focused metrics, especially the development cost part, I'd like to hear from you. Just write me a short email and I'd like to have contact with you. Yeah, have fun with the other presentations. I think there are going to be some very interesting presentations here at IWOCL. So, bye.